Welcome back to Advanced Weather Essentials, Convective Weather Guidance and Considerations. So, the most important thing I'll say tonight, and it'll be a theme throughout most of my conversation, is that we need to think convection. Many pilots get training that says stay far away from thunderstorms. I really think that's the wrong approach. I think that's missing the point. I think it will lead pilots down the path to falling into a deadly trap sometime in the future. Yes, thunderstorms are indeed dangerous. Not trying to underplay the danger behind thunderstorms, but it doesn't take a full blown thunderstorm to ruin your day as a pilot. So the real key is to minimize your exposure to deep, moist convection. So when we think about thunderstorms, we're thinking about convection. But we really need to disassociate ourselves from the fact that whether or not this convection is producing lightning or not, that's really not the point. So the primary issue or concern that we have with convection is the fact that it usually is accompanied by severe or extreme turbulence. But there always is a chance that a pilot might try to find themselves in a deep convective scenario, not seeing that there's any lightning, and get themselves into trouble. And it happens quite a bit. So ultimately, this severe or extreme turbulence manifests itself through the strong up and down drafts you're familiar with respect to convection, low level wind shear from things such as gust fronts, microbursts, and outflow boundaries, all associated with convection. Turns out that lightning is not really a huge threat when you're flying in the air. I know a lot of folks I've heard say, yes, I'm concerned about getting struck by lightning. That's really not a huge threat to most pilots. It's the convective turbulence that's going to be problematic. So you've probably all seen this diagram. It was in the Aviation Weather Advisory Circular, which was eventually consumed into the Aviation Weather Handbook. And that shows the thunderstorm life cycle. You have the towering cumulus stage, the mature stage, and the dissipating stage. And a lot of instructors, unfortunately, focus on that mature stage. Understandably so, but that's not the stage that's problematic for us as pilots. It's really this first stage, the towering cumulus stage, that building stage, that's really going to bite us. That's the one that's going to get us, not the mature stage. So, what is a thunderstorm? Well, the National Severe Storms Laboratory out of Norman, Oklahoma, came up with what I thought it was the best definition of a thunderstorm. It seems like it's a little bit silly, but it's a rain shower during which you hear thunder. Since thunder comes from lightning, all thunderstorms have lightning. The key words here are rain shower. That is the element that we need to be concerned about because ultimately all thunderstorms begin as a rain shower. You can see one here off in the distance, off this airport, in the terminal area's vicinity. This is not a thunderstorm yet. And of course, not all rain showers grow up to be thunderstorms. You can have showery precipitation and never see a single lightning strike, but that showery precipitation may still be quite dangerous. So we have to understand that the rain shower is just the beginning and likely the most dangerous part of the convective process for us as pilots. And here's the reason why. You see this supercell thunderstorm. I was in an airplane. I think it was Cessna 182, and we were flying in the central high plains, and we're flying away from this thunderstorm, this supercell thunderstorm. You can see that shelf cloud there that was moving essentially in our direction. We're flying away from that cell. But would any of you make a hard right turn here and fly right into that supercell thunderstorm? Anybody? Usually people point out, oh, it's got some, dangerous turbulence. Yes. Really, that's the result of it. But why would you not make a hard right turn there? What is really keeping you from flying into that convection, that severe convection? And again, don't overthink the answer here. Yes, exactly. It looks threatening. Very clearly, you know that that's a threat that you don't want to tangle with. And as a result of that, we tend to stay away from, and any crew will stay away from flying into something like that because it looks bad. Now, who remembers the fatal accident of Delta Flight 191 at DFW back on August 2nd, 1985? So, was this accident it was caused by a microburst, but was it generated by a supercell type thunderstorm? Exactly. This was not a supercell type thunderstorm. When you see wreckage like that, you think this has got to be a bad situation. They flew into a really dangerous thunderstorm, and that's what caused this problem or this accident. I'll go back to the previous slide and tell you they wouldn't have done that. In fact, there have been no airline accidents caused by a supercell thunderstorm for that very reason. So on April 2nd, 1985, around 6 p.m., 5 minutes prior to this accident, I'm going to show you the conditions that were present at DFW. 6,000 foot scattered, estimated ceiling was 21,000 foot broken, visibility was 11 miles, wind was 120 degrees at 8 knots, temperature was 101 degrees Fahrenheit with a dew point of 65 degrees Fahrenheit. That's pretty warm. And there was some cumulonimbus clouds to the north and northeast, which means it was more than 15 miles from the airport. So the question is, does any of this look threatening to you if you were landing at DFW? Now, this actually looks like a perfect day to fly into DFW. This was 5 minutes prior to this accident. And again, we have to beware of the benign. So two of my colleagues, Dr. Fujita and Fernando Caracena, they're recognized experts in this field of microbursts, and they've repeatedly, even before this accident occurred, and said that microbursts are frequently generated from benign appearing cells. Yes, supercell thunderstorms can create microbursts and other issues with respect to flying near them, but many microbursts are generated by those benign appearing cells. And you can see here, this is the mature thunderstorms that was in the reports up there to the north and northeast. But when you look at the DFW airport here, right in this area here, this doesn't look all that bad. There's not a lot of cloud cover in that region. There's some cellular appearance to the clouds, so you've got some potentially building cumulus type clouds. But again, this is the visible satellite image at 6:05 p.m. when that accident occurred. If you look at that temperature dew point spread I showed you, 101 degrees at the surface, and 65 dew point, 65 is a pretty juicy dew point. That temperature dew point spread, what's called the dew point depression, was pretty large. So microbursts are really common when there's really dry air below any type of cumuliform type cloud bases. In this case, they were up at 21,000 feet, which is pretty darn high. We had a broken deck up there. But essentially, we see microbursts are very common when we have that dry air below the cloud bases. And microbursts are largely driven by evaporative cooling. Essentially, at some point, the precipitation core gets heavy enough that it's released and quickly begins to evaporate below the cloud bases in that drier air, and that creates cold, dense, heavy air that accelerates down toward the surface. And so if you have that dry air below, that's going to be perfect for microburst occurrence. And here's the radiosonde observation, the weather balloon launched. It was 100 miles southwest of DFW around the time that this occurred. So while it's not exactly at DFW, it shows how the area itself was poised. And what you see here is a pretty significant signature that you're going to want to recognize. And that's called an inverted V profile. And if you took my SKU-T Weather Essentials class last year, you know how to read these diagrams. Essentially, you see we have the temperature and we have the dew point, and then the bases of the clouds are probably somewhere in this area. But you can see we've got some really significantly dry air below those cloud bases. And that inverted V tells you that. And as a result of that, that's what the fuel for microbursts, that's where it comes from. So when you think of microbursts, or maybe one that you have been shown at some point in time or seen on the internet, my good friends here from Bold Method show you this kind of visualization. It's actually probably not a great way to visualize it, so I tell folks don't think of a microburst in that way. Because many microbursts actually have a rotational aspect to them, a spiral, which makes the winds even more chaotic and therefore more difficult to overcome if you were caught in a microburst. They take you through if you all of a sudden see a strong increase in your airspeed as you're landing, you may be hit by the initial edge of that microburst. And of course, as you get under the center of it, if you've powered back because your airspeed is climbing, that's probably the worst situation to be in because now you're underpowered going into the downdraft and then eventually into a tailwind. But add the swirl to the air into that, and it makes it really, really challenging, even for the perfect execution to get out of one of these microbursts. Now, does this look threatening at all to anybody? You have some blue sky in the area. This is in Chandler, Arizona. Some blue sky out there. This is kind of a little dark cloud over there, but obviously this was taken from the ground. But imagine you were landing at an airport that's kind of underneath that cloud there. And notice the bases of these clouds are pretty darn high. So it makes it inviting to say, oh, there's the airport. I'll just go dive down in there and land, have no problems there. Yes, looks like maybe a little bit of virga or something in the area, but ultimately, this doesn't look all that threatening to many pilots. But let me show you what's actually happening here. Hopefully everybody was able to see this microburst here. Let me walk through it again. And also take note here, watch as this happens. You'll notice that that outflow really starts to accelerate off the side here very quickly once that microburst, wet microburst in this case, hits the ground. So I'll go ahead and start it again. Again, take notice as that microburst hits the ground and moves out. It really accelerates big time to the right. This was a small microburst. On the scale of microbursts, this was pretty small overall. And did anybody see lightning in this at all? This is obviously a time lapse over about a 20-minute period from beginning to end. And that microburst lasts around 3 to 4 minutes total. But there's no lightning at all because this is a rain shower, a benign appearing cell. Very common in the southwest US. But anywhere you have dry air below the cloud bases, where the bases are high, above 10,000 feet, you can expect something like this. Right, here's another one. This was out in Las Vegas, Nevada, and taken from some kind of Howard cam. But let's walk through this as well. But again, look at this. This is, some blue sky out there. Not much really going on. This might, for a lot of pilots, might think I'll just, skirt through this clear area. But you can see here that that would probably not be a smart idea. Again, very high basis to this. And that microbursts let go pretty quickly there. And once again, no lightning associated with this at all. Now here's one out of Tucson, Arizona. There's actually a total of 3 microbursts that occur, and this was probably a more serious microburst in terms of its capability to do a lot of damage. But nevertheless, no lightning anywhere in the area for any of these. So these are rain showers with lots of blue sky around. So anytime you're dealing with high base convection, can I use 10,000 feet or higher, maybe even as low as 8,000 feet, but when you start getting that really dry air below, look at that for that inverted V profile. That's a recipe for an encounter with a dry or wet microburst. Get your SKU-Ts out and look for that inverted V signature to show you have that dry air. So you can expect and understand that you don't want to fly under any building convection. I like to keep blue sky above me in these situations. So if there's a cell like that over top of the airport I'm landing at, I go elsewhere. And a dry microburst, you can't even see it. You might see a little virga right out of the base of the cloud itself, but the only way you're going to see it is if you look on the ground and you'll see actually a dust ring appear. And that's usually because there's a microburst that occurred in that area. So a close cousin of the microbursts, but it's really much less aggressive and focused like a microburst would be, and it's typically spread over a larger region, is something called an outflow boundary. And essentially, an outflow boundary is just cold, stable air, kind of the exhaust of deep, moist convection. It descends in those downdrafts, and it also cools as well, and then strikes the ground and spreads outward like pouring pancake batter on a griddle. And you can see here, using this RadarScope app, it's pretty clear that you can see this outflow boundary right here at the bottom. And that's an outflow from this convection to the north. These occur with and without convection that has lightning. You can get some pretty significant outflow boundaries associated with that. Problem with this is that most of the NEXRAD images that you're going to look at, most of them are going to filter out these outflow boundaries that I showed you earlier. And that includes even SiriusXM and FSBE and most of the heavyweight apps. They filter out these non-precipitation returns, and they do it quite well. And you can see here, this is the outflow boundary that's occurring. The convection that's just to the north and west of that is producing an outflow boundary. But take a look at SiriusXM, or the XM, in this case it was XM weather. It's nicely filtered all that out. So you're not going to be able to, on a pre-flight, power up your FSBE or power up your SiriusXM and check to see if there's any outflow boundaries coming out of that convection that you're trying to fly away from. It's probably going to be filtered out, unfortunately. And it turns out this particular outflow boundary went through my neighborhood when I was living in the northern part of South Carolina for a while. And that's the picture I got as that outflow boundary moved through. It was some clouds moving through, essentially, that developed as a result of all this. Sometimes those outflow boundaries are just clear air. It doesn't have to be clouds associated with it. But many actually produce a cumuliform type cloud or boundary, and those usually don't extend up beyond about 8,000 feet above the surface. So if you're flying at 10 or 12,000 feet above an outflow boundary, you're probably not going to feel it at all. Here's one you can actually see the outflow pretty clearly. This is over the Great Salt Lake. And you can see here that we have this outflow coming in here out of that convection, but there's a lot of blue sky around that region. And the fact that it produces a lot of dust and debris, kicks up a lot of dust and stuff, and if it's even over water, it can kick up a lot of salt spray and stuff like that in this case, Salt Lake. So this is very common to see for an outflow type boundary. I'm going to play from this RadarScope app, which I like because RadarScope app does not filter out any of those non-precipitation returns, and you can get a pretty good understanding of each one of these. You can see where the outflow is. So I'll go through and start each one of these, and you can see how that outflow boundary through there moves away from the convection. And you can actually see in this particular case, if you watch carefully enough, you'll see that some other convection develops on that outflow boundary. So if you see an outflow boundary and you're looking at it before you're going to take off and you see something like that, it's really best to work really hard at making sure that you're not going to find yourself flying through a developing area of weather. So pay close attention to the fact that these outflow boundaries are mini gust fronts, mini fronts, and can actually help other convection develop. Similar to this, you see other cells develop on that outflow. They tend to be, again, very low-level events, So if these occur pretty far away from the radar site, they tend to overshoot the radar itself. And one more here. The ones that I am most concerned about are these right here, and that is the outflow is in front and moving ahead of the convection. Those are gust fronts, and those will have significant, strong, gusty winds if you're trying to land at an airport near that where that's passing through. So an outflow boundary basically consists of an updraft followed by a downdraft. And as I said, most outflow boundaries are usually limited to 8,000 feet and below. And of course, the closer you are to the convection that produced it, the more dangerous this is. If you get 20 to 30 miles away from the convection that produced it, the outflow boundary has already lost a lot of its strength and probably won't be more than just some moderate, occasionally light to moderate turbulence. But if you're really close to that outflow when it's produced, it could be quite turbulent, severe or even extreme turbulence. And so this is a situation on the right here where they basically over a specific point, and they were using some equipment to basically measure the updraft and downdraft in the environment. And what happens here is that you can see that this line that goes through the center here, that's where air is not moving up or down. So as the outflow hits you, essentially the air is going to be moving upward pretty significant. Essentially you look at 12 meters per second, which is really at the top of this, is somewhere around 25 knots vertically. And then you immediately get into the downward flow after that. And this happens over a period of time, over essentially you can see over 3 or 2 minutes. But if you're flying through this at 200 knots, 150 knots, you're going to hit that up and down drift pretty quickly. So it's going to be one bang after another. So you're not going to, it's not like a mountain wave updraft and downdraft. You're going to hit this sort of like driving over two speed bumps right next to each other. So let's go through a case that I've gotten permission to cover from a pilot who was flying a Bonanza that ended up in extreme turbulence in IMC at 7,000 feet. In this particular case, the pilot recovered at 1,200 feet AGL. He said he was slightly on his back and spiraling down. And of course, had to divert to a small airport, overran the runway, which most of us would probably be thankful that we actually got the airplane down successfully. But you do notice here that this particular airplane, the pilot side window was shattered. And the pilot that I talked to that this happened said he doesn't know why. Doesn't know if his head hit the window in the extreme turbulence or if something in the cockpit flew up and hit it or if it was the bending or of the airframe that caused it to shatter. But essentially, this was a pretty violent event that did not have to happen. Here's the flight path. It was headed from Poplar Grove, north central Illinois, headed down to Tennessee. I think it was for a wedding, and his wife was with him at the time, and he had to divert to this small airport. And if you looked at the convective outlook from the Storm Prediction Center, this is valid essentially over the period of time that he was flying. You can see here, it's very clearly that he's going down through this area. There's not any threat of thunderstorms along this particular route. This looks pretty nice, right? This is a perfect kind of situation. I don't have to worry about thunderstorms. But you do have to worry about deep, moist convection. And that's not necessarily guaranteed when you look at these convective outlooks. You have to understand that these lines here that are shown are a 10% or greater risk of convection that essentially is looking at organized areas of convection, not necessarily isolated areas of convection. And if we looked at the surface analysis chart here, this also looks pretty favorable. You can see we have a cold front there, so we're flying on the backside of the cold front, which usually the backside of the cold front is where the weather is generally improving. And for the most part, it's under a pretty big area of high pressure. So again, if you're looking at that route, this looks like a perfect opportunity to fly from point A to point B. You forget about the fact that the surface chart is really just telling you what's happening at the surface. It doesn't tell you what's happening aloft. And so it's important, we covered this in our conversation about constant pressure charts. What you see on the left is a 500 millibar constant pressure chart. And on the right is the surface analysis chart. So now let's look at what's happening here at the surface. We see that we have some pretty warm temperatures here all along these areas. That's pretty warm temperatures. But what we see as far as the upper level weather here, this trough is cold air coming down from Canada, upper level air, cold upper level air with rather warm ground can easily produce instability showers. And that's essentially what was happening here. As this trough was making its way down through this area, it was bringing that colder air in from aloft. You have cold air with warm air at the surface, and that produces instability, and therefore you get instability showers. And as a result of that, that's really what he was running into here. This was his flight path here, showing by the arrow. And you can see that the weather, the NEXRAD mosaic that I pulled up about the time he was going through here, was showing these cellular appearance to the NEXRAD image. Those cells immediately tell you that this is a convective environment. Not necessarily thunderstorms. None of these cells are up to 30 to 40,000 feet. Most of these cells were probably at or below 25,000 feet, and most of them were probably below 20,000 feet here. Louisville had a forecast for showers in the vicinity, a good indication that they were expecting showery precipitation. And so I want to show you here, this particular cell that's circled in red was probably what he was seeing on his FSBE in the cockpit. But he allowed himself to enter into IMC, into a cloud, and really couldn't visually see what was happening around him. And so we know that the FSBE or SiriusXM weather is delayed, meaning that it's not real-time information. So as a result of that, what we could see here is that he was misguided in the sense that you can see that there's a cell that develops and moves right over to his area. This is on a short loop here. And you can see that there's a cell that one cell that was here develops and moves into this area. And of course, his path goes through that developing cell. It was developing pretty quickly, not into a thunderstorm, but essentially into what is called low-topped deep moist convection that had no lightning associated with it. We'll talk a little bit about lightning in a bit. When you have low-top convection like this, it's very common not to have any much in the way of lightning. So this extreme turbulence he ran into that turned him upside down essentially was just a little rain shower. So you really should never stop doing weather analysis. So when we look at the terminal area, that's a 5 statute mile area. That's a really, really small area. And that usually will influence how meteorologists issue their forecasts, especially as it relates to thunderstorms. So meteorologists call it a point forecast. And so when the convection is very highly isolated or scattered, don't expect to see the forecaster add TSRA, thunderstorms and rain, into a TAF. They just won't do it typically because the essential aspect of this is that they don't want to put thunderstorms in, because if they do, what ends up happening is that all the heavy iron out there has to follow an alternate and carry extra fuel. So they don't necessarily want to throw a thunderstorm in for a low probability event. But that doesn't mean that there aren't potential for convection out there in and around that terminal area. So forecasters can add a Prob 30 group for thunderstorms. That's a way for them to quantify their uncertainty. But sometimes, and most of the time, what they do is they quantify their uncertainty by adding things like VCTS or SHRA. So that's showers in the rain showers in the terminal area, VCSH or showers in the vicinity, or VCTS, which is thunderstorms in the vicinity, as a way to quantify their uncertainty without necessarily having a Prob 30 group in there. So anytime you see a forecast for showers, you have to think convection. So once again, showers in the vicinity, rain showers are very common in terminal forecasts. Notice that there's no CBs for cumulonimbus clouds in the cloud group because technically it's not a thunderstorm. So showery precipitation is often a placeholder for one of those low confidence thunderstorm events. So I always tell folks to check the area forecast discussions. In this case, it said scattered showers and perhaps a thunderstorm are expected across the North Carolina Piedmont from the afternoon until early evening and will carry VCSH for now to cover that threat. So they are thinking that most pilots understand that a forecast for showers is a forecast for convection. So forecast radar is going to become one of your best friends. If you don't use it now, I would surely recommend that you do that. For me, I utilize this probably way more than I should, but ultimately, during the warm season, you're going to find that this will give you kind of the best information from a pre-flight planning decision because it looks and feels just like a NEXRAD mosaic. So you want to look at these forecasts for that cellular type appearance, and you can see it all through this particular forecast here. You can see a cellular appearance all through here. None of this is really nasty stuff, but any one of those cells is not going to be fun to fly through or maybe even under. And you can definitely see a cellular appearance, how the colors change rapidly over a distance. So we have a tight gradient. All this is pretty much convective weather. So any of this is going to create rough air. And if you happen to be flying in the clouds below freezing, you're going to find yourself in probably pretty heavy icing because convective icing has SLD, supercooled large drop icing in it. And that's where we're going to accrete a lot of ice very quickly in these kind of cells at the right temperature. And so this is a good one to look at here because you can definitely see, looking at this, there's without a doubt some pretty nasty convective kind of stuff going on here. Down through the Gulf and into parts of northern Florida. And perhaps some of this ahead of this is maybe not as convective, and certainly the stuff to the north of this is definitely doesn't have that convective signature. So you can start to analyze this and look and understand that, hey, if I'm going through, if I have to go down into, let's say, parts of Texas and I'm here in the Charlotte area, I'm not going to find myself working myself down through the south here. I'm going to try to work a little bit further north through this area. And you're going to look at other forecasts to basically make sure and you understand that this is not going to produce any kind of convective turbulence in that sense. May have other types of turbulence associated with that, but certainly down further south is where we see the most significant weather. And we're going to look at this when we do our pre-flight planning sessions coming up in a couple weeks. And so I think looking at a forecast radar depiction really helps us understand and characterize the convection we're dealing with here. So is it going to be a line like you see here? Is it going to be an area? Going to be embedded? In order to know whether it's embedded or not, you're probably going to have to look at the ceiling forecast and the visibility forecast in the area. In addition to this, is it going to have a supercellular kind of appearance to it? Those bigger cells that occur that are kind of positioned maybe along a line? Or they're going to be a pulse type or air mass type thunderstorms that are in the area. So this really helps you kind of characterize what's happening here. And this is shown in my Easy Weather Brief Progressive Web app. So let's talk about EchoTop's forecasts from the high resolution ensemble forecast. But let me just first of all define what an EchoTop is. So essentially EchoTops are generated by the NEXRAD radars. We're going to look at forecast versions of this, but ultimately an EchoTop really represents the highest altitude of the precipitation core itself. Not cloud tops, but the top of the precipitation core itself. And so when you look at this, what you generally look at is find the 18 dBz level, and you can see my white line I've highlighted there. That's the EchoTop of that cell. And you notice that the very top of this, it's somewhere around 56,000 feet. Now we can actually do a forecast using the forecast radar depiction, but forecasting the EchoTop height, which can better help us understand if we're dealing with some really serious convective kind of clouds, or are we looking at more stratiform type stuff that's going on. So one of the forecasts I look at is the EchoTops greater than 30,000 feet. It's a great tool to kind of know where those most troubling weather is. And it's a probabilistic forecast, not necessarily telling you what the tops are. It's basically showing you what is the chance or probability. This is the probability here. So anywhere you see the reds and oranges and yellows, there's a high probability that those EchoTops are going to be above 30,000 feet from a forecast standpoint. So you can look at this over a 48-hour period. So it gives us a really good indication of where those more significant cells are going to be. And if it's not something that's above 30,000 feet, there's no chance of that. It's probably not going to be as difficult to deal with. You may be able to fly over it if you have an aircraft that can essentially get into the low flight levels. And there's also a product for 35,000 feet. So folks that are flying Citation jets, flying above that kind of stuff, that's essentially a great product for those that are flying much higher. But it tells you what the probability that the tops of that precipitation core are going to be above 30,000 feet. So here's an example here. We see on the left, this is the forecast radar depiction on the left side and the EchoTops forecast that goes with it. Both of these are from the high resolution ensemble forecast. And you can clearly see this. You can't treat these things that you see on the right side here as cells, growing cells. This is if convection develops in this area, these cells here will likely achieve 30,000 feet or higher. So these are definitely ones you want to stay away from. Whereas the ones that the cellular stuff that you see out here in parts of Illinois up into Wisconsin, not really all that high. The chances of them achieving that height is very, very minimal. So this really gives us a really good picture of how this is all going to evolve and tells us where the most significant weather is going to occur. And that preps us for what to expect en route. And you can see here that most of the significant cells are occurring on the downwind side, that nasty side of that trough axis here. So we see the trough axis right there. Most of the cells that occur that are those higher, taller cells are all going to occur here downwind of that trough axis, as we talked in the previous couple classes. The stuff that's behind this, yes, it could be some nasty, occasionally nasty areas of weather, but they're going to be less critical to worry about from that standpoint. I'm not suggesting that you would attempt to fly in any of those, especially if those are developing up in the flight levels in terms of 20,000 feet or greater. But ultimately, you look at this and you can immediately see how those more significant cells are on the downwind side of this positive tilted trough. And so here's another kind of view of this. You can see that there are clearly some areas of convection to worry about, one to the north here and one to the south. And those are cellular in appearance. But when you look at, for instance, the ECOTOPS forecast here, what you notice is that those are definitely going to be in the 30,000 foot or higher range here, whereas the ones that are further north are likely not to be in that range. So even though the stuff here looks really nasty, I can probably fly over that probably at 25,000 feet or 30,000 feet if I'm essentially in an aircraft that can achieve that. Or I can essentially, fly around these areas if I choose, but this gives us a really good feeling for where the really nasty stuff is located. So you can get the ECOTOPS forecast, radar forecast and everything at using my Easy Weather Brief app, or you can go to the NCEP website at mag.ncep.noaa.gov, and you'll see there's the ECOTOPS forecast available at that particular site. All right, let's look at one more convective product here. It's called the LAMP Convective Potential from the Localized Aviation MOS program. And it provides a really good kind of picture of what's happening from the convective standpoint because it's really an hour by hour forecast and it's very tuned into convection. This is not a thunderstorm forecast. This is a convective forecast. It really doesn't necessarily tell you that there's going to be lightning in it or not. And you can look at the other lightning potential forecast that comes with MOS as well. And you can clearly see if you compare these two, the right is the convective potential and the left is the lightning potential here. So certainly this convective potential up through here down into the south and then also up in the Pacific Northwest. But notice there's no lightning showing up here. So these are probably low-topped cells, but are convective, meaning there's definitely going to be some potential for some significant turbulence in those areas. And let me just show you the forecast radar associated with these two areas. You definitely can see in both areas there's some cellular kind of appearance. Certainly the stuff that's down here in the deep south has a more significant look and feel to it, but there are going to be some cells up in the Pacific Northwest where you're going to see some convective elements associated with this. The LAMP is updated every single hour and it has hourly time steps. So hour by hour, you can kind of see what's going to happen. Again, you can view this on the Easy Weather Brief Progressive web app, or you can go to the lamp.mdl.nws.noaa.gov site under LAMP convection.php to actually visualize that as well there. In order to get lightning, you need three basic quantities. Supercooled liquid water, you need something called graupel, which is soft kind of a hail, and ice crystals. When you have all those three ingredients in sufficient quantity, you can get lightning. But again, if you look at this around the entire area here, all these are showers. There's no lightning. I had Sirius XM turned on with lightning turned on to the Garmin Pilot, and there was no lightning showing up. These are just rain showers. And so the presence of lightning, if it does happen, indicates you have really cold cloud tops. You have deep convection going on here, and therefore you have significant vertical mixing to cause that extreme or convective turbulence. and it's also very indicative of low-level wind shear. Lightning comes in two flavors, cloud to ground and intercloud lightning. And yes, lightning can strike, like you see here, a bolt out of the blue, can certainly strike at a pretty good distance, up to 15 miles in some cases. The moral of the story there is if you can hear thunder, you can be struck by lightning. And case in point, there's a tree in my neighborhood, and I was sitting at my desk writing some articles, and all of a sudden I see a flash and immediately hear the thunder, so that I knew it was a really close strike. And our Facebook group for our community lit up and said, hey, there was a tree that was struck in Bear Park. So after that threat went away, of course, I waited for a little while, went down there, took some pictures, and there was bark at least 100 yards from where this tree was hit. And you can even see, if you look really carefully, you can see light through that center of that tree. Turns out that this particular cell that produced this lightning was over 10 miles away. It never rained a drop at this location. This was the second tree that was hit in this particular park. And almost a year to the day, you can see that stump there was the previous tree they had to cut down. Another tree was struck in the same park right next to it. And neither one of these two trees were the tallest. This one here that's standing still was the tallest tree. So it's a myth that lightning always strikes the tallest object. So this one also had to be cut down. So that's three trees in the same park. So without a doubt, I don't go to this park if there's any chance of any kind of lightning. So lightning, in terms of its cloud to ground or intracloud ratio, many locations you're going to see here, especially in the central plains here, are going to have a 10-to-1 ratio, which means there's 10 intracloud strikes to cloud to ground strikes. When you go here in the Four Corners regions, it's more of a 2-to-1 or 1-to-1 ratio, or even in the Midwest here, you'll see in the parts of the Southeast, you'll see more of a 3-to-1 or 2-to-1 ratio associated with that from a lightning perspective. It turns out that many severe storms have a very high flash rate. Lots and lots of lightning strikes are dominated by just simply intracloud lightning, no cloud to ground strikes, often more than a 10-to-1 ratio. And there are some periods where it's infinite, meaning it's only intracloud lightning. The most severe storm I've ever experienced on the surface was one where it had 0 cloud to ground strikes. It was all intracloud strikes. So it's important to be able to see both cloud to ground and intracloud lightning. But it turns out that FSBE, if you use that, it only broadcasts cloud to ground lightning strikes. So in a developing storm where intracloud lightning usually dominates the cell, you're not going to get a lot of information from FSBE. Now SiriusXM, and that's what I use for the most part, provides both intracloud and cloud to ground strikes. So it's really important to be able to see both of those. So maintaining a distance of 20 miles from a thunderstorm will prevent you from being struck by lightning. Is that in the airplane? Is that true or false? What do you think? So you're catching on. So it's false. There's nothing inherently wrong with the guidance of staying away from these thunderstorms, but it really doesn't explain how some aircraft actually have a lightning strike even when not near a thunderstorm. And it turns out the pilot can actually have 2 encounters with lightning, either being in the wrong place at the wrong time, intercepting a lightning strike in progress, or the more common one is aircraft-induced lightning. You can see here that lightning strike actually came outside of the Cessna's mirror here. And again, it's very common to see those kind of burn marks in this aircraft-induced lightning strike scenario. So again, you can actually just be in the wrong place at the wrong time and intercept a lightning strike. It's very rare and usually happens down low. And there are aircraft-induced strikes. It turns out that Apollo 12 was actually struck twice shortly after liftoff. And there was no other natural lightning in the area 6 hours before or 6 hours after the launch. And so 90% of the lightning strikes to aircraft are thought to be initiated by the presence of the aircraft itself, usually within the cloud, usually in situations where there is some precipitation occurring. So, but the scary statistic here is that 40% of all these discharges, there were no thunderstorms reported or even anticipated in the area. You were just in a region where there was some high electrical activity where your airplane itself caused the discharge to occur. So usually this occurs in clouds that are producing some kind of precipitation, um, and almost every airliner gets struck at least once for every 3,000 flight hours, which is about once every year. And so the important thing to recognize here is that most of these lightning strikes essentially happen in and around the freezing level. So if you're flying either just below the freezing level or in terms of the altitude just below the freezing level, you're probably in a position where you might find yourself getting struck by lightning. So I don't like to fly any types of precipitation events where I might be in a scenario where I might be right around the freezing level itself. That puts me at that perfect position of getting a lightning strike. Again, it's pretty rare, but it does happen. Right at 0 degrees Celsius was where the maximum is. And most of those happen around 10 to 16,000 feet. Again, in the summertime kind of scenarios that we see, most of the freezing level is right around that 10 to 16,000 feet or so. And one last thing we'll finish up is a lot of people say, well, what about flying in an area that has a lot of high CAPE? If you went through my SKU-T course last year, we define this as convective available potential energy. Imagine taking a spring and pressing it down toward the ground. You're basically converting kinetic energy into potential energy. And that potential energy, if you keep your hand on it, stays there. If you lift your hand off that spring, it'll pop up in the air. And so the same thing happens in the atmosphere. We get this essential convective available potential energy, this energy in the atmosphere that can produce convection. But just because you have a high CAPE value or high negative lifted index doesn't mean that you'll have the possibility of thunderstorms. In fact, it may be a perfect day to fly. So high CAPE does not equate to having the possibility of thunderstorms. So when you're looking at these kind of CAPE values, don't say, well, I'm not going to fly through this area down through Texas and Oklahoma. There's really, really high CAPE areas because I'm going to run into thunderstorms. It may actually be clear skies the entire area here. Not only do you need moisture, you need instability, and you need some kind of outside energy contribution or lift in order to get those thunderstorms occur. And in some cases, you can have really good area of ridge or high pressure over a region which you have substance or sinking air, which doesn't allow the air to flow upwards. So high CAPE of itself doesn't necessarily mean that you'll see convection.